well today we want to finish up our benzene chemistry. We will finish it up by, as I mentioned last time, looking at phenol and looking at some synthetic synthesis problems. So let's talk about phenol. Recall that phenol has this Lewis structure here, where we have this OH on the benzene ring. Well, if you look at phenol, it has this hydrogen on oxygen. Recall that regular alcohols in order to lose their hydrogen to become this alkoxy ion, their pKa's are around 16 or so. So not very acidic at all. We would have to have a pretty good base in order to remove those hydrogens. But coming up with phenol, this hydrogen on the oxygen turns out to be more acidic than regular alcohols. Turns out to have a pKa of 9.96. So it's much more acidic than regular alcohols. Why is that? Well, let's remove the acidic hydrogen. And if we remove it, we get that conjugate base there, where we have the O- attached to the benzene ring. Well, here, this is what's called the Phenoxy ion. And as you can see, the Phenoxy ion has special properties with it, doesn't it? In that we have a lone pair next to a pi bond. So we can draw resonance structures. Okay? So this negative charge here is resonance stabilized. Okay? So we can draw some resonance here. Where the negative charge now comes into the ring. And you can continue to delocalize that. Let's just draw one more. You get something like that, where the lone pair could delocalize once again to come down there. I'll let you draw that resonance structure. So here we see that this Phenoxy ion is resonance stabilized by all of these resonance structures. And so that is telling us that this conjugate base is more stable than that thing there. Okay? So remember the theory in that the more stable the conjugate base is, the more acidic that hydrogen was. Okay, one more time. The more stable the conjugate base is, the more acidic the hydrogen was on the acid on the other side. And so we're seeing that stability by the decrease in the pKa value. Okay? So since it's acidic, we can then remove that with a somewhat of a decent base. Say using sodium hydroxide. And this gives us the Phenoxy Ion attached to the sodium cation. So this would be properly named sodium phenoxide. Okay? So the point is we can remove the acidic hydrogen on phenol using a regular base like sodium hydroxide or even potassium hydroxide would do the same thing. You would just end up with what? Potassium phenoxide. Okay, so this is the special property of phenol. What we want to do now is look more into the acidic properties of phenol. Okay. What we want to look at specifically are ways to alter the pKa of phenol. This first way here, let's put on the ring, say, a nitro group, NO2. Remember that the nitro group is a deactivator. Okay? So what happens when I put a deactivator on the ring and we remove this acidic hydrogen? What does that do to the acidity? Does it make it more acidic or less acidic? Well, the way we can figure it out is always by looking at the conjugate base. So what does this nitro group do to this O-? Well, remember, deactivators are what? Electron withdrawing. So it is pulling on that negative charge. So doing what? Helping it to spread out, helping it to become more delocalized. And when it becomes more spread out with more volume, this thing becomes more stable. And so we would expect what? The pKa of para-nitrophenol to be what? Lower than 9.96. Okay? And indeed, it does drop down to something around 6. Okay? So any deactivator will drop the pKa of phenol. Okay? And it doesn't matter whether we put in para, meta, or ortho, any of those positions will lower the pKa. Okay? What would happen if we put an activator on phenol? Okay, an example of an activator might be something like a CH3. Okay, so if I remove the acidic hydrogen, give the phenoxy conjugate base. We get this time. And now, what is the activator doing? It is now pushing electron density toward the oxygen. So what's it doing to the negative charge this time? Is it spreading it out more? No, it's isolating it more. Okay, so the more isolated it is, the less volume the negative charge spreads out to, and so it'll be what? Less stable. So we'll have a less stable conjugate base, which means what? For the acid part, it'll be what? Less acidic. So the pKa should be higher than 9.96. Okay, and here it raises it up to 10.2. Not much of an increase. You would expect if I had a more powerful activator, it would have a higher pKa, but we do see the increase of it. Okay, and so here, this is a less stable conjugate base, so this would be more basic than the regular Phenoxy ion. And this here would be less basic than the regular Phenoxy ion. And so with phenol, this is really a neat way to tell if any group is a deactivator or an activator. Do you see that? And that you could put on phenol any group, say any of the ones that we didn't list from the chart, and you could tell if that group, an unknown group, was an activator or deactivator simply by does it elevate or decrease the pKa from 9.96 as the standard. Okay? If it increases it, then the thing was what? An activator. If it decreased the pKa, then that group was a deactivator. So a neat way to, it's a neat experiment to determine activators and deactivators. Well, since phenol is acidic with that hydrogen, this enables us to do further chemistry on phenol. We know if we react this with a base like sodium hydroxide, this gives us the Phenoxy ion in terms of sodium phenoxide. And this thing here we can take advantage of by making it act as a nucleophile. And so in my second step, if I were to bring in some substrate, remember a substrate is any carbon group that has a good leaving group. Any halogen is a good leaving group. I just chose bromine. You could have chose chlorine or iodine or fluorine. But here, you would get a nice substitution reaction. To give us this kind of compound here. And what's the name of this compound? This was anisole, remember? A phenoxy ether. Okay? So here, this is the way to make anisole that we have not learned about as previously. Okay? So here, wanted to introduce us to the Phenoxy Ion being a nucleophile to be able to attack substrates of different types. Here, for example, I made the substrate a cyclohexane ring with a chloro leaving group. So here we would get a phenyl cyclohexyl ether. Okay? So this is not a benzene, just regular cyclohexane. Okay? So this here finishes up our chemistry with phenol. Okay, so make sure you know the acidity of phenol, how to alter it with activators and deactivators, and then some chemistry with it with some different substrates. Okay? Now, there's one other reaction with phenol that has nothing to do with its acidic character. Okay? And this reaction here is a strong oxidation reaction. So let's look at how we can oxidize phenol. What we're going to do is take phenol and react it with a mixture of this here. Na2Cr2O7. This is called sodium dichromate. And the other reagent is that of sulfuric acid. Anytime you see a chromium, okay, whatever kind of compound, should always be a tip-off that that is an oxidizer. It's going to oxidize. And sulfuric acid is also a good oxidizer. So when I oxidize something, what does it do? It either what? Adds double bonds or oxygen to the molecule. And this reaction is going to do both. So you can see what it does to the benzene ring. It busts up the aromaticity. Aromaticity is gone. And we get some extra double bonds outside the ring to oxygen. And this compound here is called quinone. Quinone. Quinone is a molecule that's used in natural products. It's even found in bugs that use it to ward off enemies and things like that. But this is how we make quinone. And this is our last reaction in dealing with phenol chemistry, this strong oxidation reaction. So what we're going to do in the remainder of this lecture is now go over synthesis problems that we need to review and practice these things over and over, as you'll see these kinds of things on the exam. So let's go ahead and practice some of these things. Okay. Synthesis problems. Okay. We already looked at one of these earlier, but let's look at another one. We'll start off easy and get more difficult. Okay? So here's the synthesis problem again, where I start with this one, plain benzene, and I want to know how to make this one. Okay? Remember the two questions that we always ask. The first question is what? What is the relationship? What is the answer? They are ortho to each other. Okay? What was the second question? Which group should I put on first? Answer, since they are ortho, I want to put on the ortho para director, which in this case is what? The CH3. So I would not want to put on the nitro first, okay, because that's a meta director. So now, all I have to do is remember how to put the groups on. An alkyl group, remember, is by Friedel-Crafts alkylation. So that puts on the methyl group. And then secondly, to put on the nitro group, remember, a mixture of nitric acid and sulfuric acid. Okay? Then that will put on the group ortho. You would also get the para isomer. Okay? We can't help but to get that one too, but that's okay. As long as we get the ortho, that's all we care about. Okay? If this thing was on para, then we would have focused on the para product and made the ortho product insignificant. Okay? So, starting to get a feel of this, let's elevate the difficulty a little bit. Suppose we wanted to make this product. Let's put it over here. Okay, so here we have metachloroaniline. And we want to look at the steps of how to make this thing. Again, the two questions, what is the relationship? They are meta. Which one do I put on first? The meta director. Well, what are they? NH2 is what? A ortho para director. Chlorine is what? An ortho para director. Remember, also a deactivator. So what am I going to do here? Am I stuck? Do I say it's impossible? No. I remember that I can't put on the NH2 directly, but I have to put on first what? The nitro, and then do the Clemmensen reduction to make the NH2. So let's do that. So we put on the nitro group first. Okay? Remember the nitro group is a meta director. So at this point, I would not want to convert to NH2, but I want to take advantage of its meta directing ability to now add on the chlorine. So I have to go to my vocabulary of reactions and ask, how do I put on chlorine? Remember, Cl2 and an acid catalyst FeCl3. So that puts on the chlorine there. Okay. This should be nitro here. Okay. Sorry about that. Now, in the last step, I want to convert the nitro group to the NH2. Okay, so remember how we do that? We do the Clemenson reduction. Okay, zinc or tin, iron, and HCl. Okay, so this here was what, a 1, 2, 3-step reaction in order to get the product. Okay, so these things could be 2 steps, they could be 1 step, they could be 3 steps, 4 steps. Okay, but you see how you have to keep everything in mind. You have to know the directing ability of these groups. You have to know how to put on the groups. Okay, so that's why I've been telling you to put these reactions on note cards, so that you have these memorized, so they are very quick to use from your memory. Let's do another example. Okay, so here we want to make para-methoxy benzoic acid. Okay, this is going to be several steps. Okay, so I ask first, what is the relationship? They are para, so I want to put on my ortho-para-directing group. Okay, so I know that this comes from what? Previously an OH. Okay, and this came from first an alkyl group, and then I oxidized it with KMNO4. See how you have to have these things, these reactions in your mind, how you put on the groups. Okay, so I could put on this alkyl group first, then the phenol, or the phenol first, and then that. It doesn't matter. So let's go in this direction here. Let's put on the alkyl group. Okay. So that puts on the methyl group, which is an ortho-para director. Now I want to put on the OH, which is the precursor to that. So I have to remember my reagents, which are what? Hydrogen peroxide and HSO3F. And that puts on the OH, para. We also get the ortho isomer, but we don't care about that, so we can just discard that one. Okay. Next, let's proceed to make this the OCH3. these two steps here like this. Okay, so remember I used the base to deprotonate to make the phenoxy, and then that oxygen will do a substitution reaction. Okay, so we're almost there. So here we have para-methyl anisole at this point. And what would be the last thing we would do? Now oxidize the CH3 to the acid group using what? KMnO4. And that would give us our final product. So here, this gives us 1, 2, 3, 4 steps in order to make that product. Okay? So you want to make sure you, again, have all these reactions down so that you can pull them out of your head at any time that you need. Okay? So I invite you to practice more of these synthesis problems, because you will see at least 2 or even 3 of them on the exam. So this ends the section for benzene chemistry, okay, and it ends the section for this exam. Our next lecture, we will start with a new topic.